Today's our topic is design of induction motor, which is in subject design of AC machine. In a previous lecture, we studied about a induction motor basic principle, working and construction. Now, in this lecture, we have studied how we can design an induction motor. First of all, we have to study what is design. Then we discuss about the design of induction motor. First of all, what is the design? A design which is a systematic process in finding the dimension like diameter, length and area, some electrical parameters like resistance, reactance of a machine, and which will satisfy the given specification such as the rating of machine, speed of machine, starting torque, allowable temperature rise and various service condition. Now here is some specification regarding design of AC machine. First one is in rated output which in kilowatt or in horsepower. Second one is in voltage which in volt, frequency which is in hertz, number of phases for a single phase, for a three phase, speed which is in RPM or an RPS, type which is in squirrel cage or slip ring type, a power factor, efficiency, temperature rise, type of duty, then continuous or intermediate, specific torque requirement, a service condition and starting method. So in this subject we study about all the specifications regarding the design. Now here is some symbol regarding the design of AC machine or an induction machine. First of all, we study which type of symbol is used. First of all is a P. P which is the rating of machine and in a kilowatt. EPA. EPA which is equal to induced EMF per phase in a volt. IPS which is current per phase in a ampere. EPA which is the turn per phase. B which is the diameter of stator bore in meter. In some cases, we neglected the length of air gap, so we use B as the diameter of rotor. L which is the length of stator core. Actually, the length of stator core L which is the length of the closed length. And sometimes we use a net iron length which is called SI. A BAV which is the B average for an average value of flux density over the air gap, and the unit of flux density which is Weber per meter square. AC. AC which is an ampere conductor per meter of stator telephone. So BAV and AC, we know that which is an BAV is a specific magnetic loading and AC which is an specific electrical loading. Phi which is a flux per pole in the air gap and unit of phi which is Weber. Rho which is number of poles. So P which is the number of poles. NS which is a synchronous speed in RPM. Then here we use capital NS which is called synchronous speed in RPM. KW which is a winding factor. T pole Z total number of stator conductor, IZ, current in each conductor and its ampere, efficiency, theta which is equal to full load efficiency. Now we, first of all, for any design, for any machine, first of all we have to know about this two specific value, and this value decide how our induction motor or any machine will be designed, and the type of machine will depend on this two number of specific parameters like specific magnetic loading and specific electrical loading. Here we see that It is defined as the, first of all we see a specific magnetic loading or a BM. It is defined as the average magnetic flux density over the total surface of the air gap and is denoted by BM. So BAV, which is equal to total flux in air gap to area of flux path in the air gap. Now total flux in air gap, which means that in our machine there is a number of poles. So number of poles which is equal to P, and each pole the flux passing is phi. So P into phi, which is the total flux or total loading on the machine, divided by the area of flux path in the air gap. Here area of flux path, which means that area of rotor or area of stator. So find out this area. We have a total periphery into its length. So total periphery, which is equal to phi d, into its length, which is equal to L. So phi d, which is an phi dl, which is an area of flux path in the air gap. Now it's also called a phi by tau L. Here tau, which is equal to our pole pitch. Pole pitch, we know that pole pitch, which is equal to total area divided by total periphery divided by number of poles. So total periphery, which is phi d, divided by number of poles, which is called P. So phi d by P, which is equal to tau. Here P by phi dl, which is equal to tau. So the another equation is phi by tau L, and its unit is then Weber per meter square, because the specific magnetic loading is then flux density. So Weber per meter square, and it controls the magnetic losses as well as size of the machine and magnetizing current. Now specific electrical loading or a AC. A specific electrical loading is defined as the number of stator or armature ampere conductor per meter of stator periphery at the air gap. So here is the equation like AC, which is equal to total stator armature ampere conductor divided by stator armature periphery at the air gap. Now total stator or armature ampere conductor, which means that a number of conductor on a stator into the current flowing in this conductor. The current flowing in the conductor, which is IZ, and number of conductor, which is Z. So IZ into Z, which is a total stator ampere conductor, or it's also called electrical loading on the machine. And this electrical loading divided by stator periphery at the air gap, which is called specific electrical loading. Now stator periphery at air gap, stator periphery, which means phi into D. So AC is equal to IZ by Z, IZ into Z by phi D, and its unit is ampere conductor per meter. It affects the I2R losses. Now here we see the main dimension of induction motor, and main purpose of our design is to find out the main dimension of induction motor or any machine. By finding the main dimension, we have find the eyes of our machine. So here we see that here is our rotor and here is the stator. So length of the stator and length of the rotor, both are the equal and it's called the L. And here is the rotor, length of rotor, which is called dr, and length here diameter of rotor, which is called dr, and the diameter of stator, which is equal to d. If we find out dr value from the d, we have to minus air gap length from the d. So d minus air gap length Lg, which is equal to dr. Here is the stator and here is the air gap and here is the rotor. So we see that the total diameter d minus L, which is equal to our rotor diameter. So here the main dimension of our machine. So whole size of machine are depend on this two diameters. D and L. Now the output equation of three-phase induction motor. First of all, it is defined as the equation in which output of machine is expressed in terms of its main dimension and specific magnetic loading and specific electric loading and speed energy. So the actual definition of output equation is, in output equation there is number of terms like main dimension. So main dimension means D and L. A specific magnetic loading means BAV. Specific electric loading which is called AC, and speed which is called ns. So with these all parameters we get equation called the output equation for an induction motor. Now we derive the output equation of induction motor. First of all, we have a KVA rating of three-phase induction motor. So it is Q is equal to 3 into output voltage per phase into current per phase into 10⁻⁻3. So output voltage per phase, this means that our induced EMF which is EPH, and current per phase which is current which is called IPH, PH will be for the phase. So EMF per phase and current per phase into 10⁻³ for the kilo KVA rating. Now, induced EMF per phase equation, we know that which is equation is EPH is equal to 4.44 F pi into PPH into kW. This equation is same like as in transformer equation, EMF equation. Now put this EMF equation in output equation. So Q is equal to 3 into 4.44 F into 5 into PPH into kW into IPH into 10⁻⁻3. Now frequency, we know that a frequency F. So F which is equal to Pn by 120 for an RPM. So here is an RPS. So F is equal to Pn by 2. So put the value frequency F in the equation of output. So putting the value of frequency Pn by 2 here. So output equation is like P is equal to 3 into 4.44 into Pn by 2 into 5 into PPH into kW into IPH into 10⁻⁻3. Now in this equation we rearranging. Why we are rearranging? Because we have to put the value of magnetic loading and electric loading in the equation. So first of all we taken P. P is the number of poles and we connect phi is, so P into phi which is called P phi, which is the total flux on the machine or a total magnetic loading. Now we get the value of 3 and here divided by 4, which is called 2.22, and take 2 from here, 2 into 3 into IPH into PPH into NS into 10⁻⁻3. Now here we see that the current in each conductor which is called IZ. So here we only one circuit per phase, so IZ which is equal to IPH. Now total number of conductor in armature, it is Z. So Z which is equal to total number of phase into 2 into number of turns per phase. So number of phase which is equal to 3 and 2 into turn per phase. So here is the turn per phase which is equal to PPH. So 3 into 2 into PPH which is equal to 6 PPH. So this is equal to Z. So put 6 into PPH is equal to Z, and we get the value of electrical loading IZ into Z, total electrical loading. So total electrical loading here and total magnetic loading here. Now here we see that a flux density BAV. which is equal to P phi by phi dl. We have already discussed. So P phi is equal to dAV into phi dl. Then as an electrical loading, we already discussed, AC is equal to IZ into Z by phi d. So IZ into Z, which is equal to AC into phi d. Now put this value in above output equation. So here P phi and IZ into Z. So here we put the value of P phi and IZ into Z. So Q is equal to 1.11 kW into dAV into phi dl AC phi d NS into 10 minus 3. Now here we have all the values. We have discussed about the definition of output equation, the specific magnetic loading, specific electric loading, and main dimension and speed. Already all the specifications are here. So now here we see that a 1.11 kW, dAV, AC, kW and 10 minus 3 all are the constant, and pi square are all the constant. So d square into LNS, which is our variable. So all other constant we put on as an C0, which is called output coefficient or an output constant C0. So we put C0 here and we get C0 d square LNS. And this is our final output equation with our specific magnetic loading, specific electric loading, speed and main dimension. Now, from this equation, we are rearranging as a d square L, we found 2 by C0 NS. Or it's called as d square L proportional to 1 upon C0 NS. Because the Q is almost fixed. So its output is fixed, so it's proportional to C0 N. Which means that our main dimension is proportional to our output coefficient and our speed inversely. Now first of all we see the output coefficient, how it affects the size of muscle. In above equation here, so we see that output coefficient is inversely proportional to the our d square L or a main dimension. And if we want to reduce size and force factor machine, this will increase the C0. So if we increase C0 here, it is inversely proportional to d square L increase. D square L increase means that main dimension increase and the size of machine will increase. So if we calculate, so now we can calculate that size and force of machine will reduce with increased value of specific magnetic loading and specific electric loading. Here we see that, so from economic point of view, we should use high value as possible. However, a design engineer must also see the effect of increased loading on the performance characteristics such as power factor, temperature rise, losses and efficiency. And we should choose a value of specific loading which gives economic design and satisfied requirement specifications with good reliability. Now next one is on speed. The output equation shows that the volume of active part with the d square L is inversely proportional to the speed of machine. Here we see that a d square L is inversely proportional to speed of machine. Here we see that the size of machine will reduce when speed is higher. Speed increase, size of machine decrease. Speed decrease, size of machine increase. This is a term reduced for also. If application has no specified speed limit, we should choose a maximum allowable speed which is mechanically possible. Now we saw how the source of specific magnetic loading dAV is affect the number of parameters like power factor, core losses, overload capacity, actuation, frequency and size of machine. First of all, we see the power factor. When a higher value of flux density is taken, then magnetizing current required is large, as the magnetizing current is in quadrature with the voltage, power factor of machine becomes poor. In figure, we show the effect of increased magnetizing current IM1 to IM2. Here we see the magnetizing current increase. Now, due to the magnetizing current angle between the voltage and current phi, which is increased. So here we see the phi 1 and phi 2. So phi 1 is less than to the phi 2. So power factor cos phi become poor as we increase the flux density. So here we prove that if we increase the specific magnetic loading, the power factor becomes poor. Now second one is a core losses or an iron losses. A core losses consists of two losses, hysteresis losses and eddy current losses. These losses are directly proportional to the flux density. It can be said that core losses in any part of magnetic circuit of machine is directly proportional to flux density. So the total copper loss is equal to loss per unit volume into the volume, which is equal to loss per unit volume into area into length, because volume is equal to area into length. Now, losses is proportional to B square. So area is also proportional to 1 upon B. Now here, total because the flux density B, which is equal to phi by A. So now, area is proportional to 1 by B. So put both the equation here. So total losses per unit volume, we use B square, and area into length, we use 1 upon B. The total copper loss is proportional to B, which means that a selection of large value of B will result in higher core loss and consequently increase in temperature and decrease efficiency of machine. Now the overload capacity. Overload capacity of machine is influenced by value of aircraft flux density. A flux density is directly proportional to the area, and also higher value of flux density means large value of flux per pole, because B is equal to phi by A, which is flux density equation, and B is proportional to phi and inversely proportional to A. So if increase the value of BAV, we get higher value of flux per pole. Now for same voltage, the winding require less number of turns per pole, which means that here PPH proportional to BAV and PPH. So for same PPH, BAV proportional to 1 upon PPH. So here PPH we taken as a constant value. So higher value of flux density gives lesser number of turns. When number of turns are reduced, leakage reactance becomes small. And inductance, which is proportional to T square, a leakage reactance also proportional to T square. So diameter of circle diagram is given by P by Xc. Here Xc which is a leakage reactance. So when a leakage reactance becomes small, then diameter of circle diagram increase, which in turn gives the higher value of load capacity. Now, fourth one is a saturation. The flux density in iron parts is directly proportional to average flux density in the air gap. Depending upon the material used, maximum flux density in any iron part of magnetic circuit of machine must be below a certain limit to avoid saturation, now which in turn increase magnetizing current. Now the fifth one is a frequency. A core loss are proportional to frequency, so as frequency increase, loss will also increase. So in this case, BAV must be selected in such a way that iron losses are within the limit, because the iron losses is two parts, hysteresis losses and eddy current losses, and both are proportional to frequency. Also, the both are losses are proportional to flux density or a V average value. So we have to choose a limited value for the frequency criteria. Now the last one is the size of machine. With increase in size of machine, percentage core losses decrease. Hence, higher value of VAV can be taken for larger machines. Thus, we have discussed, we conclude that the smaller value of VAV gives better power factor, reduce losses, increase efficiency, but small overload capacity. While larger value of VAV gives poor power factor, increase losses, reduce efficiency, but larger overload capacity. So we have to keep in our mind that as a design engineer, we have to choose VAV for good performance, and the range of VAV we choose for a normal design is 0.3 Weber per meter square to 0.6 Weber per meter square. And for a special machine, we for like a cane, rolling mills, where larger overload capacity is required, so we choose VAV, which is equal to 0.6 Weber per meter square to 0.65 Weber per meter square. The VAV may be required to be reduced to lower value for special service applications, and the machine with the total enclosure, high ambient temperature, we choose. Now, in this lecture, we study about the output equation of an induction motor and some factor affecting the size of machine and the factor affecting the choosing specific magnetic loading. Now, in next lecture, we study about the choice of specific electric loading and design of stator winding and how some factor affects the length of air gap. Thank you.